Lecture 33 covers section 7.2. At the end of today's lecture, you should be able to apply our entropy rate balance equation, as well as our continuity equation and conservation of energy equations to nozzles and diffusers, coupled with the concept of isentropic efficiency. Let us recall our equations that can be used now to evaluate open system devices. We have our continuity equation, which states that the time rate of change of mass within our system is equal to the sum of the mass flows in, less the sum of the mass flows out. The conservation of energy equation states that the time rate of change of energy within our control volume is equal to the rate at which heat is supplied, less the rate at which work is done, plus the sum of the mass flows in carrying energy in terms of enthalpy, kinetic, and potential, less the sum of our mass flows exiting our system, carrying energy in the terms of enthalpy, kinetic, and potential. Now, our entropy rate balance equation states that the time rate of change of entropy within our control volume is the sum of the heats being transferred to our system per our boundary temperatures, plus the sum of the mass flows entering our system carrying a specific entropy, less the sum of the mass flows exiting our system carrying a specific entropy, plus the rate of entropy being generated. Now, when we define an isentropic process, it is one where entropy remains constant. This is an idealized scenario. In actuality, entropy will increase in any process due to irreversibilities, and as engineers, it's our goal to try and decrease these irreversibilities. Now, with an increase of entropy during a process, we're also going to have an increase of enthalpy. For instance, if we look at the figure on the left, if we go from state 1 to 2s under an isentropic process, we're going to have a large change of enthalpy. Now, in actuality, we are going to increase our entropy as we go from state 1 to state 2. And doing such, our enthalpy at state 2 is greater than that at 2s, and thus our change of enthalpy is less than if we went from state 1 to state 2s. The isentropic efficiency is defined as the actual desired quantity per our ideal quantity. That is, eta sub s would be equal to h1 per h2, the actual difference of enthalpy across our device, per h1 minus h2s, the ideal drop of enthalpy across our device.